all the way from Leicester to speak to us. And some of you will perhaps be more familiar with him coming all the way from some bake-off thing that I don't quite understand. Whatever. And anyway, Josh, in fact, has been heavily involved at the University of Leicester with setting up all sorts of exciting things and encouraging people and people of all ages to take an interest in both chemistry and the chemistry of cooking and the chemistry of baking. And he, I can see, has brought some samples for us of two sorts. So perhaps we'll be able to test his actual theoretical and practical knowledge at the end of his presentation. So thank you very much for coming, and hand over to you without any further ado. Thank you.
Wonderful, thank you very much. That is an absolute pleasure to travel over today to give this talk for you. It is going to be a very varied talk. As it's titled, The Culinary Chemist Out of the Lab and Into the Tent, and that is as alluded to because in 2023, I stepped out of the lab and into the white tent of the Great British Bake Off. I managed to get all the way through to the final. It's a program that I have watched right from the beginning. I never for one moment expected to actually be in the tent myself. And the most amazing experience, but I think what's even more amazing really is what I've been able to, what's opened up for me beyond that in terms of being able to combine my two big passions, which is my chemistry or my science and my baking. And I get to do it sort of for a living to be able to go around and sort of inspire young audiences. So it really is, I feel really, really privileged to be able to have that opportunity. So we're going to go through a variety of bits of chemistry related to cooking. But first of all, I am going to go through some of my PhD research at the start, just to show to you that I am also a researcher as well. I don't just bake and cook. So I do actually do some active research. And then we're going to go through a little bit of, just a little bit of a showcase of the bake-off. And then I'm going to go through a couple of little case studies of the sort of content that I showcase to audiences. I know I've got far too many slides that I'm going to have time to, so someone can stop me when I go too far. But I'm just going to try and show you a little bit of a showcase of as much as I can do as we go through. And like I said, we're going to get some tastings at the end, and the tastings are going to have slides to go through, sort of the chemistry behind that as we go through. Right, so the slide that I usually start off with is this. So, out of the lab and into the tent. That is because, like I said, I went out of the lab into the tent. This is me on the left-hand side in the chemical biology lab at the University of Leicester. So I did my PhD research, which I finished just about 6 months before going into the bake-off. Bake-off was far harder than writing a thesis, I can tell you that. And then that's me on final day of the Great British Bake-Off in the tent alongside my fellow finalists and then the judges and presenters. So we've got Noel Fielding, Dame Prue Leaf, Alison Hammond and Paul Hollywood. So most amazing experience. Yeah. For one moment that I think I would be in that tent, and it was it was amazing. If anyone's got any questions about Bake Off, I can give you.
It's interesting that they're all men.
Yes, we were the first all-male final for a long time. So yes. But it was the most amazing experience. If anyone's got any questions about the dark arts or the little behind the scenes, ask the questions at the end. So that's what we've got. So really what gets me into is talking about baking. Baking for me really is a science. I think you can say baking and cooking, but baking with the precision involved, all the weighing out of ingredients, the meticulous following of stepwise procedure, it really is a science. And I was looking back really as to what really got me into chemistry was really my love of baking from a very, very young age. And also that love of baking then really what started off my love for chemistry really as well. So I started off with this little reaction, which is to make aspirin. I remember doing this as a A-level student. It's one of the assessed practicals that everyone does, making aspirin in the lab. And I think for me, when I was doing that experiment for the first time doing practical chemistry in the lab, is where I really saw, actually, this is just like baking. It's just like cooking. I do this. I'm actually already a chemist. I've been a chemist for many, many years because I spend my whole time in the kitchen playing around, optimizing recipes, jotting down all of my observations and trying to perfect a recipe. And it really just is. It's just chemistry. It's just like this. And so just like we can make aspirin In the same way, we can make all of our other bakes that we do. We have our ingredients, our reagents on the left-hand side. We heat them, we mix them together in a bowl or in a flask. We heat them up. We add other additives in there. So we have catalysts, like we had sulfuric acid for the aspirin as our catalyst to help the reaction. We have yeast, which has got our enzymes, our catalysts in there to help prove and make our bread. We have things like baking powder, although not a catalyst. We add a tiny little amount to our cake, but we know that tiny amount makes a massive difference to make our wonderful risen cake at the end. So there's so much chemistry that goes on all the way through. I think also, having been on the bake-off as well, I realized quite how many of the skills I've acquired as a chemist really did help me in the tent, and none more so than things like scale-up. So doing big-scale reactions in the lab, actually, I was well equipped for baking on massive scale in the bake-off tent because I had to bake like I have never baked before. So having to zest like 15 lemons at one go and work with 40 eggs for one bake is nothing like I'd ever done before. And it's when you were practicing for that you realize how, just like when you're doing scale-up chemistry, doing things on big scale, things take longer to weigh out. It's longer to wash up as well. But all the reactions take longer. There's lots of considerations to take in. The yield maybe not be as good. The overall end product might not be as good. So it's actually having had those experiences and knowing what works well and how to sort of adapt and work on the fly really did help me in the bake-off tent. So that's a little introduction to baking as a science. Like I said, I want to talk a little bit about my research first, to showcase you that I am a chemistry researcher. I don't just cook. So I've got a few slides first on my research at Leicester, and there's going to be a few little foodie links along the way. So I'll just a walk. So my PhD research, and there's my first sort of year and a half of postdocing, was on making PROTACs. These are called proteolysis targeting chimeras for a class of enzymes called HDACs, or histone deacetylase enzymes. So these HDACs, they are these airpogenetic regulators, and they catalyze the hydrolysis of these little acetyl groups from lysine residues of our histones. Histones are existing. So if we have here's a cell here in the nucleus, got our chromosomes. Chromosomes comprise of our chromatin fiber, and that chromatin fiber is made up of this optima of histones with this DNA wrapped around it. And the histones, which are in green, they can be subject to a variety of different post-translational modifications, which can signal for example here, gene activation, gene repression. They can have methyl groups on here. We can have acetyl. We can have all sorts of different groups on here. But the HDACs are looking to take off these little acetyl groups. So what my research we're looking at being able to create these molecules which could inhibit this HDAC just here. So the HDACs, there's 18 of them in the human genome. These are split into two different families. And we've got these NAD plus dependent and the zinc dependent ones. The zinc dependent is 1 to 11. They're the ones that we were focused on, in particular, HDACs 1, 2, and 3. These HDACs, they are overexpressed in many different cancers, especially colon cancer, and we're looking to target them in a manner which hadn't been done before. And how we wanted to target them was because these HDACs 1, 2, and 3, they exist as part of these multi-protein chiropressor complexes. So these multi-protein complexes, and you'll see that there's 7 here. These 6 that have got HDAC 1 and 2 in, they exist in these different ones. It's really hard to target individual HDAC enzyme isoforms individually, and given that they exist in these different complexes, what we wanted to try and do is trying to target a particular complex and do it using what we call these PROTACs. So these are the different complexes. Like I said, use these PROTACs. What is a PROTAC? A PROTAC, it's this bifunctional molecule. It's got 2 warheads. So we've got an HDAC inhibitor at one end. We have a E3 ligase ligand at the other end, and that'll come in. I'll explain that in a moment's time. And they're linked together by this linker. And what they look to do, these PROTACs, they look to target a protein and degrade it. So instead of your classical inhibition approach where you would bind and inhibit a target, it's still there, you just blocked it. These molecules look to bind, engage with it, and then they degrade it and they knock down levels of that protein altogether. So how it works with here's the PROTAC. It engages with your HDAC on one end, and then the other end engages with this E3 ligase. This E3 ligase is this sort of like cell quality control sort of machinery. So it helps sort of like engage these proteins, and then they will mark them to be degraded. So this is this ternary complex that we've got, and by bringing this PROTAC has helped to bring these 2 close together, so that what happens now is we have a lysine residue here. It can be ubiquitinated, happens once, it can happen multiple times. It creates this tag, and this tag of this polyubiquitin tag stamps your protein to be degraded. So it gets degraded by the proteasome, and now you've knocked down the levels of it altogether. This cycle can happen catalytically, so you can release the protein again, and it can do multiple cycles of this degradation. So instead of just inhibiting, we're looking to degrade the HDACs. And as part of my research, I made the first examples of PROTACs to target these enzymes, these HDACs1 and HDACs2. So to showcase to you what some of the molecules look like, we'll go through that. But before I do that, I mentioned about cake. So I did actually make my ternary complex in cake form. So here is cake. I think this was during the pandemic. There was a craze going on with my research. Here is my ternary complex in cake form. In terms of like the chemistry involved, what the molecules look like, well, this is called CR994. This is a class 1 HDAC inhibitor. So like I said, it's most of the inhibitors that are known. You can get like HDAC1, HDAC3 selective inhibitors, but we can't target these complexes selectively. That's what we were looking to try and do with this work. So what we did, this particular inhibitor here, this is it sat in the active site of the enzyme, and this little acetyl group that I've got with the red box around, it's surface exposed, so it points out. And because it points out, we sought to functionalize off from that position and make it into our PROTAC. So we add the linker and this E3 ligase ligand on the end, and then that makes our resulting PROTAC. So there's a lot of work that's gone into this little orange arrow just here, but here is an example of an active molecule that worked. So you've got your two warheads with the linker together. And then this is a Western blot to give you an idea of what the protein levels are in the cells that we're looking at. So I did all of the synthesis of the molecules. I did all of the cell work as well. So it was a really wonderful PhD project to go and do, because I got to see right from concept through to end result. And this is the Western blot, so you can see your HDAC levels, and you'll see this is with the PROTAC. As we get more concentrated here, you can see that it's completely fading away. So we're completely degrading that HDAC. And then you'll notice here, this is with just the inhibitor, CR994, and you'll see there that the levels go up, because in that case there, it is just inhibiting it, so it's engaging it, so it's still there, but it's not working, so that there's more, it's synthesizing more of this HDAC to compensate for its loss of activity. So you see it go up, you see the levels go up. So that's like 10 micromolar of the inhibitor, and it's at 164, 10 micromolar of a PROTAC, and it's down at that. So you can see that we've successfully degraded it. So that was a little snapshot of the research that I did. And the reason why I wanted to mention it, because it connects quite nicely into sort of like how I approach my baking as well. So I mentioned this arrow was a lot of work in that arrow. So here's just a few of the molecules that I made, just a small sample of them. This is my PROTAC library. And so what we did in this case here, this is very much like SAR. So we had structure activity relationship. So at the first point, we changed the linker. So the big part of this PROTAC technology is quite hard to predict what's going to be an active degrader. So what you have to do is you'll need to sort of like optimize each component part of your molecule. So we first of all look to, I changed the linker type, and you've got a variety of different families there. Then we changed the warhead here, so you've got different ones there. And then we changed the other end, and there's different ones there. Don't worry about looking at them in detail. There's a lot on that one slide, but just to showcase to you, that's all of that's 2.5 years worth of work condensed into just one slide. That's what chemistry is all about. But the reason why I wanted to show that really was because actually going about doing that, making molecules to then go and test, it's all about fine-tuning and optimizing along the way. A big part of the molecule stays the same, but a small part of it then is just changing, just to try and find those little tweaks as to what works, what doesn't work. So in the same way that's my PROTAC library, here's my cake library. So actually I can take, again, there's a lot of overlaps between the two, whereby actually in many of these cases, there might be the same flavor sponge or the same sort of type of decoration going on into each cake, but I just change a little bit each time to try and get a little bit better and try something a little bit new. So that's the cake library. That's just some of the ones I've done. So it's a little bit old, that slide now, but that's some of the ones that I've done. But I've also got my macaron library. So some of the macarons that we've done. You can see my chemistry themed one just there. And then likewise here is my pastry library. So again, a lot of the time the pastry might be the same recipe. So like my PROTACs, like 2/3 of the molecule stayed the same, and I've just optimized one component part. That's the same as what I'm doing here. So actually, as a baker in the kitchen, as a chemist in the lab, the same skill set going about sort of like try and optimize a compound or a recipe, notes as to what worked well, what improvements were there, and if it doesn't, go back to the drawing board and try again. So yeah, there's a lot of parallels between the two. So that sort of nicely now, so you've gone through most of the chemistry now. So if people, I know if there's people who haven't seen chemistry before for a little while, that's the bulk of it now. We're going into food. So that's that part. So I thought that segues really nicely now into talking a little bit about the Great British Bake Off, as that's what most people probably have seen me from. So the Great British Bake Off, here's a little highlight reel of some of the things I did on the show. Fortunately, I got all the way through to the final, so I've got lots of weeks to showcase, but I just pulled out a few little things. This was the bake we did on the left-hand side, was from the semi-final, making this Italian puff pastry layered sort of like a dessert. Had loads of fun doing that. This is my biscuit illusion burger, which I've got on the next slide as well. And this one was the one that I got the famous Hollywood handshake for. We have a bread. This one here was a tiger bread for the Leicester Tigers, because that's my rugby team. I play rugby as well. I noticed the wonderful rugby posts here at the university. And then we've got other ones as well. I've got my chemistry chocolate box. So it was great fun to do all of that. And I've learned, it took so much of the skills that I've got as a chemist in the lab to sort of help me get through that and devise those recipes. And none more so than to sort of showcase to how my scientific approach to doing the bake-off. I've got this one here disassembled to showcase to you how very, very methodical, very, very laid out. We had to make your favorite meal in biscuit form as an illusion. So I remember I sat down with my brother when we were putting this one together, and we said, what should we do? We looked through our phone, looked at the sort of meals we have when we go out places, and we saw burger. So, well, we'll do that one as the one. But actually picking that one worked really, really well, because you had to try and challenge yourself by picking as many different biscuit types as you possibly could to try and put that together. So there was a sweet potato fries that was actually an orange shortbread with a cinnamon sugar to look like seasoning. We had a Florentine burger that was a Florentine dipped in chocolate to look like a burger. There was an almond bun. There was some sugar biscuits here, a gingerbread chopping board. So it was great fun to put together. But I think you can see how that sort of scientific approach to having it all beautifully laid out and putting it together, actually assembling those recipes and sort of like tweaking them and optimizing them, I absolutely loved it. It was the best part of the whole process. But even better than that, I actually got to bring chemistry to the bake-off itself. So I think you saw it on a couple of slides before, but I brought my chemistry chocolate box in on week 4. Now, it went a little bit over their head, I will admit. And unfortunately, that is my only real negative that I take away from the show, really, was the fact that this didn't get very much showtime on the episode itself when you watched it. And it was sort of like brushed away a little bit when I had the judges coming over. I remember talking to Prue about this box, and she was just like, oh, Josh, you've lost me at the last roundabout, is what she said, and I can't really engage with it. And it was a real shame, because I was trying to sort of showcase my passion for my subject, which is chemistry, but I was trying to talk about it in a way in which was really relatable to any audience, because I thought that when this goes out onto Channel 4 and on a television program, it'd be amazing to have just the general public to have young people be able to look at this and see this is the chemistry that's actually behind everything that we eat. So, like I said, we had the chemical elements to spell out different words along the side. We have different chemical structures on the top. I haven't got enough time to go through them all in detail today, but we've got all sorts of ones. We've got some fatty acids, we've got our bicarb, we've got the structure of vanillin here as well. So we've got lots of different ones. This is maltol, which you'll find in your caramel. And I explained it all in a really nice way that hopefully anybody could follow. But unfortunately, when you see the edit of that program, you don't see very much of it. But I think that probably sums up how sometimes like television sort of sees sciences, and especially chemistry. I think it's really hard to get chemistry showcased on a television. It is a complex subject, but I was trying to try and demystify some of those bits that people are scared about with chemistry and try and showcase it in a nice way. That's the only negative I have to take away. So there's my chocolate box. Like I said, we had to do chocolate truffles in there as well. So I spelled chocolate out with my chocolate truffles. So it was a lot of good fun to put together. You can see we've got chemical cutouts as well of different glassware. And in fact, the glass stands the box sat on was made by our glass blower in the chemistry department. And the wooden board that sat on was actually out of the undergraduate labs when they had a refurb over the summer. So it was chemistry through and through. It was a really great thing to do. So that's all about Bake Off, and I thought I'd just do a little tangent now and talk to you a little bit about what I've been able to do post Bake Off, and then a little bit about the sort of like talking a little bit about the chemistry of cooking, the chemistry of baking, what I get to go and do and give out and talk at shows and at schools and colleges. And that really stems from the fact that, so I work at the university, my role there is split, so I still do some research in the lab, but I also have a role as the academic sort of science communicator and public engagement champion. And with that, I have got the science kitchen, which was an old cafe, got converted into the science kitchen. It's adjacent to the chemistry building. This is what it looks like. So we've got, I do workshops and all sorts of events in there, and it's a real nice blend of the chemistry and the kitchen all together. So I've got a variety of, we've got all the models in there, but we've got, you'll see there's a bit of a stirrer hot plate there. We do some bits and bobs in there. We've got a nice analytical set of scales, but also got all the mixers as well and do everything. So it's using the chemistry equipment to do baking with, and yeah, it's been a lot of fun. So I thought I'd talk a little bit about how that came about and what my sort of direction of what I want to do with that. And for me, really, I have that and the science kitchen to really try and access all strands of chemistry. Whether I'm talking to Key Stage 2, GCSE A-level or undergraduates, it's all about being able, for me, to be able to use cooking and baking to be able to access every single bit of chemistry that we can possibly do. And I believe that I can access all of that. So as you saw, my research wasn't necessarily food science, but for me, it's really being able to use the universally accessible medium of everybody loves to eat, everybody loves to be in their kitchen, and it's being able to use something that people are really familiar with, really accessible, to try and talk about the chemistry that the kids are learning either at school or for undergraduate level chemistry as well. And I believe we can access all of that. So even just yesterday, I was doing a webinar on organic chemistry, on the chemistry of life for A-level students. And for that one there, what we did is we talked about how we have over 20 million organic compounds now, all the different sort of properties and states, and so much different organic chemistry, but all of it, actually, we can collect a lot of it through just everyday life, what we eat, what we drink, and we can talk about all those different organic structures, and it's a really great way to explain it. So things like terpene aroma compounds, so we talked a little bit about that, and therapeutics, natural products, these are all organic compounds, and we can all have a little sort of connection to food, drink, or medicine. And we talked about dyes as well. So this is alizarin, which is from the madder plant root. We've got vitamins, we've got sugars and carbohydrates, we've got fats and oils, amino acids, proteins, enzymes, DNA, all examples of organic compounds, and I can access and talk about all of these through the sort of talks that I do. So I have a variety of chemistry experiments, some food ones, I might get to taste it at the end, and I get to talk about all those different organic compounds, all the structure, the composition, the reactivity, and I do it all through the medium of food. So a few of the things I get to do with the Science Kitchen. So I mentioned webinars. I've done a variety of webinars. I put this slide in because I thought if there's some bake-off fanatics out there, I've had a variety of bake-off stars to my Science Kitchen. Both these actually are also scientists as well. So I had Jürgen Klaus, who's the German baker from Bake Off a few years back. So actually last year for Pie Day, then 14th of March, we did the physics of pie. And for International Women's Day last year, I had over Dr. Shabira Youssef, who actually did her PhD in genetics at the University of Leicester. And we did sort of like the structure, function, and discovery of DNA. And we did a chemistry one for bread as well. I do quite a few webinars with Chemistry World. So it's been really great fun to do all of those. Alongside that, do lots of baking shows. So here's a variety of some of those. This was just at Norwich Science Festival a couple of weeks ago, and that was on the stacked science of pancakes. But I've been able to present at the RI, at Edinburgh Science Festival, New Scientist Live, Cheltenham Science Festival, do all manner of different talks to all different adult audiences or to young people's audiences. And it's all about the chemistry behind sort of like things we're familiar with in our kitchen. But we can talk about some real hardcore chemistry, and I'll usually pick 2 or 3 key themes, and we'll have lots of experiments along the way. I also do lots of outreach at schools. So this is the real amazing bit that I take most joy from the role, is being able to go around to schools, and I'll go and do a talk to different audiences in the day. So might go and talk to the chemistry students for A level, but I'll also go and do a more broad science talk to the whole school, and then might go into just from last week actually at the pastry school, talking to level 2 and 3 pastry students, and we did actually live demonstrations as well. Done quite a few bits with the NSPCC. We had Johnny Ball over before Christmas as well to do bits into the maths field as well. We did engineering connections with making a gingerbread, and I get the kids up to do lots of the demonstrations along the way. And then finally, also I do quite a lot of stuff on Social media, because that's where all the kids these days, they're all on their phones, where they get a lot of their information. A lot of that information is not very accurate. So I like to try and showcase some really visually captivating videos that we have that are connecting chemistry and science with cooking or other sort of like topical science stories. So we do a variety with the new scientists. So this is obviously a lot of the chemistry and science behind baking. But equally, we also do a series with the National Space Centre, which is called Mission Bake, which we recently won an Arthur Clarke Award for. And this one here, we sort of like use cooking and baking as sort of like the vehicle to help talk about topical space stories or artifacts at the National Space Centre, or all sorts of manners of different science as well. So we have things like meteorites, where the composition of the meteorite connects to the composition of a real meteorite. And we had a trifle that was mimicking the layers of the Europa moon of Jupiter, all sorts of different things along the way. So it's a real joy to do that with the Science Kitchen at the University of Leicester. So after that, I thought what I'll do now, I'm going to quickly go through now just a couple of the sort of like case studies of the sort of the shows and bits I get to go and present. One of them will connect to the cake that we're going to get to try. So this first one is about the cake. This is a spiced pumpkin cake. And where I'm going to start with this one actually is, alongside my love of baking, cooking, and the science, I quite like a lot of heritage as well. I also grow all my own fruit and veg at home. But I love looking at old recipes. And so in our archives at the university, we've got this old manuscript written by Rebecca Dixon. It's around about the late 1700s, early 1800s. And in this book, there's over 270 recipes, typical for any book of that sort of period, beyond just cooking like dishes and bakes. There's recipes for dyes, all sorts of very strange remedies. There's things for wine and all sorts of recipes that are packed within this book. It's beautifully handwritten. There's 4 or 5 different people you can see it written in the book. And one of the ones that I pulled out is this one here. It's called Pomatum for the face, some sort of like face cream that they're going to have made. Line 1 says, take the fat of a well-fed cow calf of the cauldron. So I like to show this one to when I go to audience, talking to young people, because it's like, I read this, it's a little bit like a witch's cookbook, the way in which it's written. And it's just really showcase how really, like, the way a lot of the pages are written, it's like reading almost like a chemistry manual, really, and a procedure. So, for example, at this point here, into this galley pot, they add 3 sliced marshmallow roots, 3 blades of mace, and it sounds very much like Harry Potter-style potions class, where we sort of chop bits up and put them into a pot. But it's really just showcasing how that sort of art, what we're doing in our kitchens, is very akin to just how we are operating in the chemistry lab. And it's also what's wonderful to see in the book is you'll see where they've crossed out recipes and they've made either an improvement underneath or said, this is no good anymore. So you can see there's that chemistry sort of nature of, that methodical nature of trial and error and sort of optimizing the recipes along the way. But within that book, there's a lot of recipes with pumpkin or with spice or gingerbread. So I sort of combined all those together. I made my own spiced pumpkin cake. This is it as a loaf cake. I've done it as a tray bake for today. The ingredients list is here. I can probably put that up at the end if anybody's worried about what's in it, but I will be talking about it. And the recipe is available if anybody wants to make it themselves. It's very, very tasty, so I recommend doing so. I haven't used my own pumpkin this time because I've just used my last pumpkin from what I grew last year, so it is tin pumpkin. But it's a fabulous recipe to do. So what I usually do in my shows is I'll usually start off with a recipe, and then we'll just pick out a few of the sort of core sort of chemistry principles that we can explain behind each one. And I know that I was forewarned that there might be a few teachers or schools watching today. So I sort of like got a variety of different sort of levels of chemistry that I was going to talk about for this particular cake. So I'm going to start off with real basics as to what helps our cakes to rise. We all know we put our bicarbonate of soda into our cakes or our baking powder. And what it's doing is either via the heat of our oven or by reacting with an acid in our mixture, we are going to be creating carbon dioxide and water. Carbon dioxide creating the bubbles to help give our cake a rise. Water, again, it will just vaporize in the heat of the oven, help to give us a nice lift for our cake. It's great to talk about when I talk to students, because it's just really to get them familiarizing with the acids that they have in their kitchens, because we've got 4 examples here. We have got one that's coming out of a bottle. We've got one that's buttermilk, one that's a white solid, one that's a fruit, and they're all got acids. They're all completely different types of acids. We've got acetic acid, we've got malic acid, citric acid, ascorbic acid, lactic acid, potassium ditartrate. So we've got all sorts of different acids, and we all have these in our kitchens Well, they're in the fridge or in a cupboard, and we all use them in our baking. And a lot of the times when I go and speak to the audiences, they're not really aware that they're using these acids all the time and why they're using them. So that's what we've got. And that's a balanced chemical equation to go alongside it. And then if we focus on that bit where we had our bicarbonate of soda plus our acid, if we were to take those two together and put them into one pot, that would give us our baking powder. Our baking powder has already got our acid in the mix and sort of anti-caking agents or padding agents, so they don't react. And sometimes they'll have two different types of acid in there, like one that will act quite quickly and one that will be a late stage one to help give that cake a little bit of a boost halfway through the bake time. But we've already got those in our mix, add them to our cake mixture, and it helps give a rise. Usually I will set these out and I'll have 4 or 5 different bottles with different acids in, and we'll add the bicarbonate of soda with a balloon on top so we can blow those up. And then we set it up as a proper chemistry experiment. So we'll have a negative control, we'll have one that will have just water in, this will do nothing, and then we'll have one with water and our baking powder in, and that will inflate. So it's a really nice way to talk about how we set up a chemistry experiment, but doing it in a really easy and familiar environment. So that's the first bit. Speaking of the raising agent that we've got our bicarbonate of soda. But on the topic of chemical leaveners, so this is the one that we tend to use now. Originally got from mineral deposits from sort of like dried out salt lakes, now made industrially through the Solvay process. But before that, because I like to mention about heritage recipes, used to use potassium carbonates, or sometimes referred to as pearl ash in the recipes. I've got quite a few recipes where you see pearl ash written as one of the ingredients. And then also before that, used ammonium bicarbonate. And if you look in a lot of the Scandinavian recipes, you will see it will say ground hartshorn or ground deer antler. That's where there's high levels of this ammonium bicarbonate or baker's ammonia found in there. But in each case, again, it's great to talk to a student audience about how the carbonate is a familiarity there. That's what's producing our carbon dioxide. It's just a counterfire that we're changing in each case. And for the last case here with ammonium bicarbonate, the side product that we get is just ammonia. So actually, you end up with you can put lots of that in and you'll get absolutely no aftertaste whatsoever, because the ammonia gas will just dissipate. But the bottle itself, when you take the lid off, does smell very bad. Whereas these ones here, if you've gone overboard with them in your mixture, you'll know about it. So that's that. What I usually also talk about here is a little bit about the pH scale as well. I often talk about, we'll have our range of different, we talked about a little bit about acidity there. I usually use blueberry juice as my go-to demo. And we talk a little bit about pH as a measure of acidity, and where some of our ingredients and things that we have in our kitchen, where they sit on that pH scale. So we've got our bicarbonate of soda sits up at 9, and we've got water here at 7. Our lemon juice and our vinegar sit obviously down the acidic end of the scale, 2 and 3. Also, a great point to talk about how the pH scale is a logarithmic scale. So just because you see a difference of 1 on the pH scale, actually it's a 10-fold change each time. So actually, if you're going from an orange may sit here, and you think, oh, it's only a difference of 2, but actually it's a 100-fold change. Now, at the other end, we've got things like egg is slightly alkaline. That's because if you've got the carbon dioxide that is in the egg, once it's gradually sort of dissipates the pores of the eggshell and it's lost, the carbonic acid that it would be when it's in the eggshell, as that's lost, it slowly makes the egg is slightly alkaline as a result. Then we've obviously got things like soap and bleach, and then we've got our bench acid and base, hydrochloric acid and sodium hydroxide. And the reason why I set this up again is because I'll talk a little bit about the synthetic dyes that we have that make up our universal indicator scale. But in the same way that we have that, we have lots of things in our kitchen that are also natural pH indicators. So, for example, red cabbage and blueberry are 2 classic pH indicators that we have naturally. Red cabbage is one that's done a lot at schools, but I really love to use blueberry. Blueberry works absolutely fantastically well. So I usually take around a little bottle of some blueberry juice, and I'll put it into some water, into some acid, into some alkali, and you'll see the drastic change. And then also you can follow it up with a recipe as well. So if you make your muffin batter, if you put some lemon juice and lemon zest into one of them, and you leave it I usually leave it overnight first, then I'll bake it. You open that muffin up and the blueberries are bright red inside, really, really jammy. And it also works really well with pancakes as well, so you do it like that. But likewise, if you were to not add the lemon in and you just put in an extra teaspoon of bicarbonate of soda and leave it overnight, if you then bake that muffin or fry that pancake, the blueberries have gone green on the inside. and it tastes disgusting, so don't eat that one. But it's a great example of just showcasing chemistry in action. That the colour is down to the anthocyanins, the pigments that we have in the skin of our blueberry in that case. But it's a really good demonstration of showcasing. We're covering a lot of different chemistry there. We can showcase the chemical structures and talk about pH, how that molecular structure changes, and why we see different colours as well. So actually, I think I put the slides in for that one today. So on the blueberry one, when I go and give the talk, I'll usually give the talks. So depending on the level of the audience, so if it was for a sort of key stage 2, key stage 3 audience, I'd probably stop at that. But if we're talking to a GCSE A level or into undergraduate level, we can begin to bring in like, how do we see colour and how is that changing? So we'll talk a little bit about the electromagnetic spectrum. I'll talk a little bit about how in our visible light region, here we have our visible light region, and how different solutions, how we see that colour. So in the case of a liquid solution like this, so let's just take this one here, for example, it's going to be those anthocyanins, for example, they could be absorbing in that region of the spectrum. Whatever light is remaining that's passed through, that's the overall colour that we see. So we're absorbing in that region, down there. This passes through, the solution looks like that. We can then apply that to our system. Here's my 3 blueberry ones that I've got. And then I've been and used our UV vis spectrometer, collected the results from that. One thing to bear in mind, the scales are the reverse here, but it's great to showcase how we can have the facilities that we have at the university, how we can apply them to this case. So you can see for this one here, which is the acidic one, we have a lot of absorbance in this 500 region, so around about here, but this passes through, so it looks red. For the one that's over here, which is in the alkaline conditions, we're now absorbing in the 600 region, so up here, but we're not absorbing down here, and that's where we've got an overall green colour. So we can showcase the chemistry in action and actually run some results live and showcase them what's happening. So it's a really great way to be able to scale it up from whether they're sort of like under 11 all the way through to undergraduate level. So that's a little bit about pH and colour. This other one that I brought in for this one is on the science of flavour. And this sort of connects a little bit about how we talk about where our ingredients come from. I figure being at the university is a perfect place to be giving these types of talks, because you've got young adults that are just they're just becoming independent for the first time, having to cook for themselves. It's really great for them to use fresh ingredients and know where their food comes from and to try and eat healthily. So in this one here, which is our spiced pumpkin cake, what I've done for this recipe is I've jam-packed it full of all sorts of different spices and flavourings as we've gone through. And just to showcase to you how we get these flavours and these spices from all manner of different parts of plants. So all we've got there, we've got cinnamon as a bark, we've got ginger as a tuber, we've got our allspice here as a dried fruit, we've got nutmeg as a seed, we've got clove as a dried flower, we've got pumpkin as a fruit, and vanilla as a pod. So it's 7 different parts of a plant, and they're all bringing their own little bit to the party to give this overall wonderful flavour. So it's really to try and talk to the students about what is flavour, because flavour, it's not just that taste of cinnamon. There's so much more to the flavour of cinnamon. There's hundreds of compounds and volatile aroma compounds in it that make up that flavour. If I just pull just one flavour in particular from just each of those spices, here's some of them. So we've got gingerol here, fresh aromatic flavour that we've got in our ginger, cinnamaldehyde, warm spicy flavour in our cinnamon. But that's just some of those compounds, those flavour compounds that are pre-existing in here. But there's so many hundreds that all come together, and they overall make up that wonderful, it all just all marry together and make a lovely flavour. That's hopefully what you'll taste at the end. Alongside talking about the flavour that's inherent into our bake, we can also create flavour and colour as well. And that's where we bring together the ingredients we need for that. We need some sugar, we need some protein, and we need the heat. Bring all that together, we get a complex series of reactions, our Maillard reactions, and we can help get lots of different flavour and aroma produced, and we get the wonderful colour as well from these melanoidins. And that all comes together. Like I said, sometimes I'll present this as a slide like this to a generic audience, but also we can go into complex detail, and we can talk about some of these flavour compounds that we'll also see as well. And we can go through some of those complex series of reactions and how we get to each one. So it's a really great way to build up and use the same talk, but just to do it in a different style. And then, like I said, I like to try and utilize different facilities at the university and just take it that one step further and sort of apply it into a research setting. So for this example here, we've got a pumpkin cake. I've had to slice it open. We can see, hopefully, a really nice internal structure of our cake. But in research, if maybe we're looking at some archaeological object, maybe we're imaging a person, and we want to look at the interior of these, we can't go slicing people up or slicing these or slicing up our objects. So we have to use other means. And what means do we have? We have things like CT imaging. So this is a way of non-invasively being able to get these cross-sectional sort of slices of an object, where we've had to actually invasively cut that open. We can do it using X-rays as well. So for this one here, I've taken a pumpkin, we've imaged it under our micro CT scanner, and we can try and build up what the internal structure of our pumpkin is. I've got a little video to hopefully show that as well. So this is from top down, so that's the stem of our pumpkin first, and you'll see it gradually build up, and you'll see slice by slice as it comes through, and we should be able to reveal the seeds that's on the inside of our pumpkin. But I find this is a great way when I speak to the students to talk about how we can translate. So here we're having to physically cut something open to reveal that structure, how we have techniques to be able to see on the inside of objects without having to invasively cut them open at all. So it's a really nice way to sort of to gradually build into some really complex chemistry and science to talk about. So that's it with a pumpkin. So everybody is familiar with a pumpkin. We know what's on the inside of a pumpkin, and then we can also translate it to some research as well. So what I've got here is this is some research by Professor Richard Thomas at the university on some Egyptian mummified cats. And this case here, this is usually done as a Halloween show, so it works quite well for that. But you can see here, bit by bit, we can see as we're looking on the interior of that, and from these sorts of images that we build up all together, we can learn about the sort of the life that they lived, the mummification process, and the diet that they had. So they can learn all of this out from being able to do this CT imaging. So it's a really great way to use something like food, which are all very, very relatable, we all understand, but you're to segue into talking about some really complex research as well. So I don't know how I'm doing for time. How are we doing for time? Yeah, okay. I'll do a little bit on chocolate because I'll finish with chocolate because that's also what we're going to have. So I'll do a couple of slides on chocolate now. So we've got the cake, talked about the chemistry of flavour. What we've also got, we've got some little tempered chocolate discs which I put on the top. I like to do chocolate because it's one of those ones you watch the Bake Off, you watch MasterChef. It's one of those core techniques is doing your chocolate tempering. So I've done that. Hopefully there'll be a nice shine on the back and you can have a little snap of it. And it's engraved with the logo of the University of Leicester as well. So I've gone the extra mile. But we can talk a lot about it. There's so much wonderful chemistry to talk about with chocolate. So I'll try and go through them at a good pace. We've got here is our chocolate. What's it composed of? What we've got sugar crystals, we've got cocoa solids, if it's dark chocolate, not for white. We've got milk solids, and they all sit in a sea of cocoa butter. And the cocoa butter is really, really key when it comes to the tempering process. Cocoa butter chemistry, again, so we get to talk a little bit now about fats. So when I talk to student audiences, they'll definitely have encountered triglycerides, probably at the top end of GCSE into A level. So again, it's something that they are relatable with, they will understand it. So we've got here's a fat triglyceride. We're going to talk about what being composed of 3 fatty acids and a glycerol backbone. We can showcase it in the chemical structures as well. This put here, I usually talk a little bit about how we've got saturated fatty acids, or we've got unsaturated ones. Unsaturated because it's got our unsaturated carbon-carbon double bond in there, and it's that unsaturated bond. I left my molecular model in the car, but when you've got those ones, it creates a kink in the molecule. By having a kink in the molecule, it means that those molecules, they don't pack together quite as well. And as a result of that, the melting point's lower. As a result of that, they exist as oils at room temperature, as opposed to solids that you would have for your saturated fatty acids. So you'll get a lot of saturated fats in like animal fat, in like coconut oil, but things like nut oils and things have got a lot of unsaturated or polyunsaturated fats. As we add the unsaturation, we lower the melting point. We have these nice, healthier unsaturated fats. So that's with those. And then now that leads really nicely into our chocolate tempering. So I said that the cocoa butter is really critical for that. It's because we've got to be able to melt it and we've got to get it to crystallize into a particular form. So this is a bake-off classic, is being able to temper chocolate. Now, historically, chocolate week on the bake-off is always on the hottest weekend of the year. It was for me. So I'm going to tell you how we temper chocolate, but do not do it in a 40-degree temp because it's not very good for it. So what we do, chocolate tempering, you'll see it happening on these shows. I was watching MasterChef The Professionals the other night, and they'll be doing chocolate tempering there. It's where we're taking our untempered chocolate, our soft, dull chocolate, the one if you've got a bit of dairy milk from the supermarket, and we can heat and cool it in a particular way, and we can get it into this tempered form. We can improve the properties, so it's really glossy. It's nice and firm. We can construct with it. You saw the chocolate box made earlier. It has a wonderful shine. It has a perfect snap. So hopefully, maybe if I've got I'll take one of these. Maybe it's going to let me down now. If I hold it up to here, it's quite a thin disc. You get a little snap. That's what we've got. So, and we're going to do that. So, but to get to that, I need to talk a little bit about that cocoa butter and the chemistry involved. So, like I said, the cocoa butter, it crystallizes in different forms, and that is what's critical to our tempering. So, I've done this nice and pictorially to hopefully explain it in a really nice way. So, the cocoa butter, it can crystallize into 6 different forms, 6 main ones. I've labeled them from 1 to 6 just here. So, let's just say here's a generic chocolate that we've started off with. It might have a mixture of all different ones in there. Mixture of crystal structures. But when we get to our tempered chocolate, what we've done is we've just isolated this particular one, form 5, and that has got those perfect properties that we have this wonderful shine, wonderful gloss, wonderful snap. The way in which it crystallizes, well, these molecules stack up in different ways. This is another example of how we can take it to one little level higher. So this is your free fat molecules. We've had our melted chocolate, and then they can pack together. We can get this double chain packing, the way in which these molecules stack up. That's often found in forms 1 to 4. And then we get this, what's called this triple chain packing for forms 5 to 6. It gets a much more stable form, and that's why it has these wonderful properties. So it has got that firmness, and you can build with it. So if you make big panels of it, you can stack them together, and you can make these big constructions. And you can also you will cast like chocolate truffles and things with them as well, and you can pick them up and they won't melt in your fingertips. So the properties of those different crystal forms. So here are the 6, 1 to 6 going down here. Here's the melting point. The melting point increases as we go from 1 to 6. They're more stable, they're more dense, the way in which they're packed together. We've got here some of the properties for each one as well. And like I said, it's type 5, which is the perfect one. That's what the chocolatiers want. It has the perfect properties, wonderful shine, wonderful gloss, a wonderful snap. And the melting point is just such that it will just melt wonderfully on the tongue. And if you leave your chocolate a bit longer, it'll eventually go crystallize into this type 6. Very, very hard. Does not melt very well. It can become quite gritty. But that's the one that we want. And the reason why talking about tempering is such a great topic here is because we temper in all sorts of different industries. So we can temper metals as well in exactly the same way. We can heat and cool the metal, so we can get particular properties. If you want particular durability or hardness of the metal, we'll heat and cool it in a particular way. It's exactly what we're doing with the chocolate. So here is a little sort of like a graph now to showcase it in action. Here is the temperature scale. This is what, if you get a bag of quality chocolate and you look on the side, and it'll talk about tempering, it will have some very precise temperatures that you must hit. That is what we've got here on this scale. So here's your starting chocolate. We heat it up first. We melt all of those ones just there. Then as we cool it down to 27, usually around about 27, 28 for milk chocolate. And then that's encouraging now just those type 5 that I mentioned to grow. You'll see the temperature just there. So at 27, we should just be really beginning to sort of get type 5 to crystallize, maybe get a little bit of 4, but mainly 5. We then heat it up a very small amount, 1 or 2 degrees. When we take it up a little bit, we now definitely melt this one, but we haven't get to this temperature. So we're just encouraging just type 5 to sort of crystallize out. And then we just leave that to set, and we end up with our wonderful tempered chocolate. You can also seed your melted chocolate as well to help encourage the crystallization. I usually bring a bit of sodium acetate in a bottle, which is a really great example of a chemistry example whereby if you have a saturated solution, 1 little seed crystal of sodium acetate, and that's what you've got in your hand warmers, and it will suddenly crystallize out. Exactly the same way here. You can get, if you get pre-tempered chocolate and you melt a little bit of that, mix that into your mixture, it'll help it to set quite nice and easily. Or if you get really high quality chocolate like the Calabo or Belcolade chocolate, they're usually often pre-tempered. So a lot of their recipes to do temper quite quickly. You'll melt 2/3 of it, maybe just chuck a third in, and you just do the temperatures a bit quicker like that. But it's another great way of doing so. So that's chocolate, and then I think that brings me almost to the end. I've got 2 last slides because it connects quite nicely to a book that's going to be coming out tomorrow. I've written a bit of it. So like I said, I choose lots of different, we've done CT imaging, done UV vis, I've done a lot of electron microscopy work as well. This is my sourdough starter. We imaged it under an electron microscope. I was a Gemini 1. So we prepared the sample. I've got other slides to talk about how we actually prepare the sample. We prepare it using critical point drying. It's a really great way of preserving the biological detail, using supercritical CO2 to do that. But what we do is we prepare the sample and we go and image it. Usually, I haven't done for today, I'm sorry, but I'll usually bake a sourdough. I'll chop it up and everyone can taste it. I let them eat it first, then I show them what the starter looks like, because if I show it them first, it doesn't look quite so good. You might sort of regret that decision. But if we zoom in now on what my sourdough starter looks like, this is a bit under an electron microscope. So it's pretty amazing. We've got these like big starch granules. We have got our individual yeast cells. We have got our lactic acid bacteria in there as well. These are all living and thriving in our sourdough starter. And it actually links really well to how I did my PhD research. I did my chemistry in one building, did my biology in another building. And the biology was cell culture of my colon cancer cells. So the way in which you look after and culture cells in an incubator is exactly the same as looking after your sourdough starter, in that they are living and they are growing, they're multiplying, and it gets to a point where you've got to then take a little bit out, put it into a new pot or plate, and then they're going to grow again. So with the cells, I will harvest those cells and I will just aliquot a little bit onto a plate. Same with your sourdough, because they are multiplying all the time, then every day you're going to take a little bit out, put it into a new pot, add a bit more flour, a bit more water to feed it. The cancer cells will be adding a little bit of media, so I can feed those as well. And you'll see that the yeast cells, they'll have these sort of like edges on them where they're sort of like budded up. That's when they are dividing, those bits there, those flat edges where they're budded and divided. And then we can look at it. Here's on an even zoomed in scale now. This is 1 micrometer. That's great to talk to the younger audiences about as well. To get a feel of scale, because when we're usually talking about chemical structures, we're talking about molecular level. Most people, they're familiar with what they've seen. So this is now going on to a microscope level, but then obviously on the chemical structure level, we're talking even smaller again. Here we've got 1 micrometer. The width of one of the hairs on your head is about 70 to 80 micrometers. So that from there to there is probably 10. So that 7 or 8 times is just the width of one of your hairs on your head. That's how small we're looking. Look at one individual yeast cell. And like I said, the reason why I mentioned that is because a lot of these images are in this book, which is going to be coming out. I think it's out tomorrow. It's led by Matt Hadlard, who, if you don't follow him on any social media channels, he's an amazing self-taught patisserie and baker. He's absolutely wonderful. So all the recipes in there are his, and then I've done all the sciencey bits. And a lot of the microscope images and things that are packed within that book have all been captured by the amazing technicians that we have at the University of Leicester. So it's another great way to sort of give a voice to those technicians that are really invaluable. Anybody that's worked at university, you'll know that the technicians are the people that help keep the departments running. So it's great to be able to give them a bit of a visibility. You'll see their names mentioned on all my slides as well, people that have helped me along the way. So that brings me all the way through to the end. Hopefully that's been a nice sort of journey all the way through, doing a bit of PhD research, a bit of bake-off, a bit of chemistry behind cooking and baking. You've learned about the science of these, this pumpkin cake and this chocolate, and then you're going to get to eat it now. So thank you very much.
Thank you very much for that. That's brilliant. You are an amazing ambassador for chemistry. You really are. Gosh, you've taken us through the whole syllabus tonight. There must be questions. So, any questions? Right, here we go.
You have the formula for vanilla on the screen. Are people wasting their money by buying natural vanilla or synthetic vanilla?
So actually, I've got a project going on that right at the moment. So actually, obviously, the flavour of what you're getting in your vanilla is so much more than just the vanilla. So the vanilla is a very small component. You've got all the sorts of polyphenols, the fatty acids. There's all other bits that are part of it that are adding these sort of creamy and other sorts of flavours in there. So yes, a lot of the synthetic or just the vanilla essence that you will see is probably synthetic vanilla added in, but it hasn't quite got the full character, and you can tell on the resultant bakes. One of the biggest ones I find is something like Dr. Oetker vanilla that you often find is a really syrupy, gloopy one. I find that one, if I put that in a cake, you cannot taste it at all in your bake after. If you do that one compared to a proper sort of like vanilla extract or vanilla bean paste or actually vanilla pod, you do them side by side, you'll be able to tell which one's got the proper vanilla in.
Thank you. Madagascar vanilla tastes different to the other types of vanilla?
Yes.
Certainly more expensive.
Yeah.
Shall I start passing?
Oh no, I need to put I'll put a little chocolate coin on top of each one, then they can go and okay.
Hello. I'm a secondary science teacher,
Oh,
and if there were one experiment I could do with the students I teach, which would really inspire them and bring food together and science together, what would it be?
Oh, which one?
Starting from scratch.
I think for me, I like to piece together a couple of little bits. I cut into a recipe or a bake. So if you just did bread or you just did a cake and did the little ones along the way, I think, like I said, I mentioned the classic one of your bicarb and vinegar, which is the one that everybody will see as the big erupting volcano, and it's done really for show. But actually, if you take it down, like I said, do a set of different acids, do one that's just water, one that's water with baking powder. You can set it up, experimental design. You've got ones that work, you've got a negative control in there, you've got one where you've already got the acid in there, and you've used 3 different types of acid. One's come from a fruit, one's come out of a bottle, one was a solid powder. So a really great visual way to showcase chemistry in action. Any of the sort of like color changing or pH ones are another great one as well. I did mention that the blueberry one's a great one because the red cabbage is your classic one, but no one likes red cabbage, especially when you start with the younger ones. So if you do blueberries, everyone loves a blueberry. So that's a really great one to do as well. So they'll be my 2 main ones.
Hi, there's a few students here tonight who are taking A-levels and then thinking about what degrees to do. What A-levels did you do, and what was your first degree before you were postgrad?
My A-levels were chemistry, biology, maths. Chemistry, physics, maths, but chemical biology is afterwards. So I did chemistry, physics, and maths because I was very broad. I loved my biology, but for me, I liked a particular part of biology. I like human biology, but not everything else all the time. So I did those. I went to study pharmaceutical chemistry at Leicester. That's why I picked Leicester. I know it is my local university. I'm from Leicester, but pharmaceutical chemistry, sort of like drug design, drug development, is what I really got a liking to, mainly because it has that sort of design, that developmental approach of being able to design molecules and then go and test them. That's why I wanted to do that. So my PhD was then chemical biology, doing the ProTech work. So yes, that fed into that. And what was the second part to your question? Sorry.
That was it really. What was your A-levels and what was your degree?
Yeah, so
you didn't do biology A-levels.
I didn't do biology. By doing pharmaceutical chemistry, I picked up the biology. The biology that I loved is the biology that I did as part of my degree course. And it's wonderful when you can pick degree courses or options where often for chemistry, for example, maybe the first year or first year and a half will be broadly the same for everybody, but then you can have the opportunities to be able to then go and diverge beyond that. So for me, it was chemical biology, but some people there's forensics chemistry as well, materials chemistry, and chemical engineering, so you can sort of diverge beyond that. But I think the grounding in chemistry, absolutely fantastic. And I've done a lot of work over in the biology labs, and we always say, we love it when the chemists come over because the chemists understand everything and they're really good in the lab. So actually picking up doing all the assays and things, they're brilliant at it. It's when we have the reverse and we're bringing some of the biology students into the chemistry lab, it's a little bit more challenging than the way around.
So, follow-up question on that: if you had your time again, would you choose the same subjects?
I was having this conversation with you earlier. I was wondering maybe I should have done food. No, I should have done food science. Maybe I could have done food. I never did food tech either at A-level, so I did or GCSE. But I've always had a big passion for it. And when I go and talk to students as well, because I think sometimes when you talk to the younger people, they could be a people pop them in, and it's about they are the siloed as to whether they are really academic or really sporty or want to go in the food route. Whereas for me, I just love a bit of absolutely everything. So I love my sport. It's the best part of the week, playing rugby at a weekend. I've always loved my science, always loved my chemistry. I've always loved my cooking. I love a bit of everything. So yeah, I couldn't do everything at the GCSE level, but I've been able to pick along the ways. And the physics understanding it from A level was absolutely invaluable for chemistry as well. So and then, like I said, the biology I was able to pick up on. So I sat on many pharmacology and physiology modules and things with the biological sciences degree course whilst I was as an undergraduate. So yeah, I learned a lot from those.
I've done a bit of a head count. And then one or two people may have to go without. Or
I've got 4 more spare.
Got 4 more spare, in which case. So if you'd like to take one, we'll move along.
I might just move it to find I might try and find the recipe so you can just make sure that you're all okay with everything.
I think most of us here, if I'm giving advice to the next generation, chemistry is so important. So if you have to drop a subject, biology is easier to pick up than chemistry.
And then the other thing with chemistry is that I look back actually just because I anticipate the questions when I go out to give talks. I went back and got back in touch with all of the people that I studied my chemistry degree course with, and it is incredible to see how a chemistry degree course equips you for such a wide, vast variety of careers beyond chemistry. The skill set that you get, because you've got the independence, you've got the writing skills, the presentation skills, the lab work, being able to work under pressure, being able to look at the health and safety component of being able to run those experiments, the problem-solving component. There's so much that you get packed within a chemistry degree. It really does equip you. If you're unsure quite what direction to go down, pick chemistry, and then from that you can go and do anything.
Yeah, I quite agree. I did chemistry. I ended up teaching nuclear physics. Just a branch of chemistry anyway.
If I'm cooking, I tend to think about the texture and the flavour. You're telling me that you concentrate a bit more on what's going on with molecules and things within the mixture that you're making.
Yes, now when I'm doing it for the bake-off, now I know that Prue Leaf, number one on her list is flavour. Flavour is number one. So every single week of the bake-off, I would be taking in all the fruit and veg from my garden. Because anywhere that grows their own, you'll know that you cannot get better than what you grow yourself. So every week, I basically had no fruit or veg that I ate myself in the garden. It all went into the bake-off. So all the fruit went in, and you planned your recipes for the first 9 weeks before you did any filming. So I actually, just me being me, I was looking at the dates when everything was being filmed, and I was writing down which fruit will be in season each week. So I'd be like, so week 7, my strawberries will be about perfect then. So week 7 was strawberries and cream. At the start, we filmed in April at the beginning. So I know I wouldn't quite have fruit ready, so I did things that had like Black Forest jams and things. So I was using fruit from the freezer. And then in week 9, I did a Christmas themed week. I did some Christmas sausage rolls, and I usually make I made a cranberry sauce. Usually I'd use pork, but I use my own homemade wine to make this cranberry sauce.
So science, strictly speaking, can come into that week, or that area.
Yeah. But I'm always thinking about how I'm putting together the design of being able to put together the flavours, yeah. But yeah, it was wonderful to talk through with the judges a little bit of the science behind it. Don't think Paul was really having any of that.
Flavour is everything.
But yeah, flavour's number one. So I always brought in my own fruit and veg, because if you didn't bring it in, it would be provided for you. But the orange that you have bought and you have tried and tested may be very different to the orange that they'll buy in for you. So I want to make sure that the flavour was absolutely bang on. So I brought a lot of things in.
I'll do one quick plug for food science and say that the students never went hungry. So when you're doing a degree, it's worth thinking about that. And you were telling us when we were talking earlier that you help the undergraduates eat healthier. So.
Yeah, that's why it's so beautifully placed being at the university. So obviously I'm there. My main love is for chemistry, and I do a lot of this to talk about the chemistry that connects with lots of things we have in our kitchen. But on the other side of things, it's a university board role, and it's really being able to make, whether it's budget-friendly meals, but using really good ingredients and just educating what food's good for you. So we've got wonderful botanic gardens at Leicester as well. So sort of we do lots of things through there. We have a seed library at university, so students can pick up free seeds. So I've got then a variety of recipes that use these seeds in those recipes, so they can pick up the seeds, take them to their residents, they can grow them, so they can grow some cress or some rocket on their windowsill, and they can go and use that into their recipe as well. So it's really wonderful to bring it all together.
Now, I believe, tell me if I'm wrong, Colin, that the Royal Society of Chemistry is offering £1 million to the first person who can make a chemically free cosmetic. So there you go. If you can come up with a chemical-free cosmetic, there's £1 million for you.
It'll be a long time.
So, have we more questions?
One more question.
Hi Josh, just while you were talking, I didn't know you were a gardener. Have you any tips as how to get the best flavour from the stuff you grow in your garden? Is it down to the seed, the variety, or soil, or how you treat it?
Soil is a big part, so I do make my own compost as well to use that. That's always great for it. Sometimes it's down to where it's its location as well, where you're growing it as well. So again, as a scientist, when I'm growing a new variety or a new plant, I might grow 3 or 4 of them, and I'll put one in the greenhouse in a sunny spot, one in the shady spot, one outside, one somewhere else, and just sort of like I like to document things to see how things grow and think how things react. Because certain spots of the garden might grow better than other. But in terms of flavour, yeah, it is feeding it well, really good compost, and don't have them too close together. As tempting as it is, something that I've learned as well, because I just will love to cram as much into a bed as I can, but give things space, and it just worked well.
So 2 apologies we have to make. One to our Zoom watchers, that they can't taste this.
Oh, I understand. I'm very sorry.
And the other is we did try very hard to get the Yellow Bookshop in Tetbury to bring your book today, because we know our members like to have signed copies. But as you quite correctly said, it's not available until tomorrow, so we couldn't do it. But we did try. But that isn't to say please do go to the bookshop, and tomorrow it will be available.
Yes, Science of Baking, and I've had the joy of being able to co-author on that series from Dorling Kinders is wonderful. So there's science of, I helped write a bit of science of flavour, science of fermentation. Before I was in it, there was science of cooking, the science of gardening, the science of spice. They're a wonderful series, just for the general audience. So it's got the chemistry of the science in there, but it's just got great visual reads as well. Really good.
Thank you very much, Josh. No more questions? Then can we thank you not you all? Thank you very much.
And the recipe's available, so you've got no excuse not to make it yourself.